Good evening, all. Good evening, and welcome to the second week of the online summer school on quantum computing. I welcome Dr. Kulkarni sir, who joined from America. Welcome back, sir. I welcome today's host.
Good evening, Bala.
Good evening, sir. Good evening.
Madhu.
Good evening, sir. How are you?
Vandana. Vandana, ma'am.
Good evening, sir. Good evening.
Yeah, so nice.
I welcome Reshma Desai ma'am. She is today's host. I also welcome Dr. Vandana ma'am, today's speaker. I once again request all the participants to submit your assignment.
Reshma. Good morning, Reshma.
Hello, sir. How are you?
Yeah, so nice. This is morning here.
Okay.
Yeah.
So this is evening here.
Yeah. Missed you for 3-4 days.
Yeah. Yes.
I remind all the participants to complete all the quizzes and assignments. That is the eligibility to get your certificate. With these few initial words, now I hand over the proceedings to today's host, Dr. Reshma ma'am.
Yeah. Thank you, Dr. Madhusudan. And good evening, everyone. And welcome once again to this National Online Summer School on Demystifying Quantum Computation. So in the last 5 sessions, we have learned quite a lot about quantum computation, starting from superposition, then quantum bits, some experiments to create superposition. And in the last session, we have learned about quantum cryptography. And today we have Professor Vandana Luthra, who will be speaking to us about quantum gates. Before I invite her to start her session for today, let me once again give you a brief introduction of our speaker for today. Professor Vandana Luthra, she is hailing from Gargi College, Department of Physics. She's also the course coordinator of this workshop on demystifying quantum computation. She has qualified for national level NET, LS, and CSIR examinations. She is a recipient of the Meritorious Teachers Award, NCT, Government of Delhi. Let me just see what's happening here.
Yeah. Please carry on.
Yeah. Okay. Yeah. So our speaker for today has won Meritorious Teachers Award, NCT, Government of Delhi, Indian Association of Physics Teachers prestigious award, which is Dinbandhu Sahu Memorial Award. She is one of the 4 digital literary champions by College of Open Learning, DU, under UKI ERI Higher Education Strand, and the Excellence in Teaching and Research Award by University of Delhi. She has got Trusted Reviewer Award by IOP UK. She has guided 5 PhD students and has published more than 36 papers in international journals of repute and has contributed chapters in 8 books. She has a Whale Boys Cast Fellowship, DST, at University College London, UK, and Raman Fellowship at Binghamton University, USA. She has been a visiting scientist at University College London and works in material science, nanotechnology, and conducting polymers for diverse applications. Professor Vandana Luthra has trained many teachers on research-based pedagogical tools across the country, again, which were organized by ISER Pune, British Council, and DBT. She was nominated to participate as a master trainer in effective pedagogy for Delhi Science and Technology Cluster under the Office of Principal Scientist Officer to Government of India. She has been resource person for workshops on interfacing of physics experiments, research-based pedagogical tools, machine learning, and computational physics. She has acted as chair, panelist, session judge, and plenary speaker in various conferences. She has also initiated Own a Mug, e-waste sensitization and awareness in her institution. This is a brief introduction of our speaker today. Before I request Dr. Vandana Luthra to begin the session, I have a few instructions to all the participants. Kindly keep your mic in mute condition. If whenever required, that is only when you want to ask a question to the speaker, you can unmute yourself. Also, the quizzes that are posted during the session and towards the end of the session, make sure there that you answer them within the time limit. This will lead to your certification. It has been already informed to all the participants that 80% participation in quiz as well as your regular attendance is a must to get the certificate. So with this, a few instructions, let me now invite Professor Vandana Luthra to kindly begin her session. Welcome, ma'am.
Thank you so much, Dr. Reshma. Thank you so much, Dr. Madhusudan. It is initiated by Dr. Kulkarni. Welcome you, sir, again back in this session. And thank you to all the seniors who are gracing the sessions from, I think, very beginning until now, and the enthusiastic participants. I will be failing in my duty if I don't acknowledge the teamwork of all the resource persons, Dr. Abha, Dr. Rajiv, Dr. Jyoti. Tomorrow we will be having a session by Dr. Kiran and Dr. Balakrishnan, who is always there for us to nudge into any difficulty we face in. And the team of volunteers and team of also volunteer is there, and also the observers. And thank you so much, Dr. Reshma and your team, for the wonderful back support which we are getting, front as well as the back support. Thank you so much. So I share my screen and I begin my talk today, which is going to be on quantum gates. Is my screen visible?
Yes. Okay.
Am I audible?
Yes, you're very much clear.
Okay. I just need to pull this somewhere so that
I'm trying to find out from where this.
Yes. So the talk, we are having a sessions in demystifying quantum computing for secondary school students and beyond. And today is our 6th session. I think my mouse is working fine. Just a minute. Yes. So we had 6 sessions until now. Today is the 6th session. We had on superposition, and my one other session was on qubits. And in that, we talked about transition from classical bits to quantum bits. In between, we also had talks about how to create bits using superposition, using the beam splitter in one of the sessions by Dr. Jyoti. And in another session, we had superposition 2, and in that, we talked about the Stern-Gerlach experiment by Dr. Rajiv. We had a session on quantum cryptography by Dr. Abha Khandelwal, and today we are going to have a session on quantum gates. So in this, I am very tempted to always read these sentences which always motivate any one of us. That is by Richard Feynman. In spite of incredible achievements, Feynman thought of himself as an ordinary person who studied hard. According to him, there is no miracle people. It just happens that they got interested in this and they learned all this stuff. That is just people, according to him. And I have no special talent. I am only passionately curious. These words by Albert Einstein also are pertinent for the cases that curiosity drives many inventions. And it is also said that any beginning is the most important, rest will follow. and a beginning has happened in this workshop. And we will be having a team of 100 ambassadors after the workshop is over. And that is what I would say beginning has begun. So quantum computing is a field which is interdisciplinary. I am again just sliding through these slides once again. And it will rely on many fields. It is not only mathematics or material science, it is an interdisciplinary field. So knowledge of all these subjects is also very important. We had, and there is again a recap that we talked about classical systems and quantum states and what is the differences. In qubits, we talked about classical computing, number system, realization of gates, and then we talked about classical bits and how to transfer, say, bits to information, followed by the discovery of diodes and transistors as the benchmarkers for the classical gates operation, followed by many Nobel Prizes in these areas by many many scientists. And we also talked about a pair of scientists, one scientist who actually had done who had got a double Nobel Prize, and that is because of this discovery as well as the BCS discovery. And we talked about the classical gates and then their truth tables and the simulations using that, followed by how does a diode, how does a OR gate can be implemented with the help of diodes. And that simulation, I hope that all the participants must have seen other simulations also, which were shared in the group. And then we talked about quantum bit, and then what do we mean by superposition, and what are the properties of the quantum bits. In that, we also talked about the normalization condition, and normalization condition would say that mod of alpha square plus mod of beta square is equal to 1. And this was a case which is alpha times the 0 state plus beta times the 1 state is equal to the superimposed state. And this superimposed states play a very important role until the measurement is done. And after the measurement is done, there is a definite state. So here we talked about an unbiased coin. And in unbiased coin, that if the probability of occurrence of a tail or head is not equal, and in that case, we talked about the unbiased coin also. And here, when we are talking about quantum bits, we talked about the direct notation. And in direct notation, we talked about that how to write these bits as a combination of, say, columns and rows. And here, one of the important condition and how to create these quantum bits with the superconducting quantum dots, trapped ions, neutral atoms, NMR, silicons, and photons and polarized photons are the different ways in which we can have the physical realization of the quantum bits. Here, important video I had shown that was on superconductors, that how superconductors and their theory is also playing a very important role in the basically superconducting qubits. So far, so good. And revision checkpoint also we had. Today, our talk is going to be on introduction to quantum gates, mathematical operations, and some computational insights into this. And then quantum gates, and I will be talking about poly X gate, identity gate, Y gate, Z gate, and a little bit about C0 gate, and other gate is the Hadamard gate, and then summary and question and answer. So why gate-based implementations are important? Gate-based quantum computer use quantum gates to transform our initial quantum states. These quantum gates can be represented by unitary matrices, and experimentally these gates may be applied using mirrors, using beam splitters, as we have already seen before, and other methods such as laser pulses sequences. These are different methods through which we can manipulate quantum gates. So in this case, important property of quantum gate is that these should be unitary in nature. What do we mean by unitary? I understand that we have an audience which is mixed audience. And in that case, it is very important that we try to do these things with hands-on practice to tell that what do we mean by, say, unitary operations, what do we mean by matrices, how do we do operation on matrices. So I would also request all my participants to kindly keep a pen and copy along with you so that anything important when you are listening, you can also try here. So in this case, suppose is my screen visible? Is my screen is visible? It is blank is at the moment.
Yes, yes. Yes, it
Yeah.
is.
So if I have got a matrix, it is an arrangement of elements in a sequence. So suppose I have got an array of numbers like 0, 1, 1, 0. So, and I'm labeling it as X. If I want to transpose this matrix, then in that case, I write XT. And what does it do? I will convert the order of the rows to column and column to the rows. So can I get to know that what will be the, in this case, the row is 0, 1. So it will become column, and another row is 1, 0. So that will also become column. So this is called transpose. After transpose, we also do a, say, conjugate of this particular matrix. So if all the elements are real numbers, then in that case the conjugate becomes the same. So it will be 0, 1, 1, 0. And now this is called X dagger. Once I have done the transpose and I have taken its complex conjugate, I call it as X dagger. And if X into X dagger is equal to I is here the identity matrix, then we say this implies X is unitary. So we need to multiply X by X plus or X dagger. Here I would also like to mention here that this is a 2 cross 2 matrix. So when I multiply a 2 cross 2 matrix with another 2 cross 2 matrix, then the number of columns of the first matrix should be equal to the number of rows of the second matrix. And the resultant matrix is 2 cross 2. So now we should multiply X with X dagger. So let's do that. I can choose a rubber. Okay. So matrix multiplication also plays a very important role in this. And then we will be trying this using a Scilab code. So here, if I again choose my pen. So here, if I have got my X to be 0, 1, 1, 0, I was also getting my X dagger to be the same in this particular case. So 0, 1, 1, 0. When we multiply a matrix, then in that case, as I told you that this is 2 cross 2 and this one is also 2 cross 2. So here this 2 cross 2 will be, after the multiplication, we are going to get another matrix of 2 cross 2. In case the column of the first matrix does not match with the row of the second matrix, in that case, we cannot multiply that particular matrices. So all these, those who are in school, they will be studying these things in their higher classes. So right now, let us apply the multiplication here. So when I multiply, then in that case, please use this horizontal multiplied by this vertical multiplication. So for the answer, I will request please don't annotate on the screen. This is visible. So in this particular case, the first here I want to have the first element after the multiplication. So what I will be doing 0 into 0 and 1 into 1. So if I do 0 into 0, answer will be 0, and 1 into 1 will be 1. So I am getting first at this element as 1. Then I find the element at this position, which is the first row and second column. So for that, what we do 0 multiplied by 1 and 1 multiplied by 0. So can someone write in the chat what will be the answer? 0 into 1 and 1 into 0, addition of these two. Can I get some answers in the chat? Yes, 0. Correct. Dr. Krishna Kumar has written, yes. Okay. So we have got here 0. And then for the third position here, this is our second row and first column. So 1 into 0 plus 0 into 1. So what we get is again another 0. And for the fourth position, it is 1 into 1 plus 0 into 0. So we get our answer as 1. So this is nothing but 1, 0, 0, 1. Correct, Ruchita. So in this particular case, this is called an identity matrix. Identity matrix has got a special property that according to the dimensionality of the matrix, this is a 2 cross 2 matrix. All the diagonal elements are 1 and rest of the elements are 0. So if I write a matrix like this, 1, 0, 0, 0, 1, 0, 0, 0, 1. So what is this? This is an identity matrix of order or of 3 cross 3. And same way we can write for so many others. So if x into x dagger, so here we did a multiplication of x into x dagger and I am getting an identity matrix. It means that x is a unitary matrix. Is this point clear to everyone? Can I assume that it is clear?
Yes, madam.
Okay, thank you so much. Thank you. And here today in this session, we will also be using Scilab online. So if in the Google, you just write online Scilab, an application appears and that application is capable of taking all the commands and executing it. So I will be just showing that in just a moment from now. Let me just rub it so that I first give a command. How would I execute this code in a Scilab? Those of you who are having 2 devices, they can always practice in one device. They can work or try the Scilab, or you can note it down right now and later on you can try to apply this or practice this. In the Scilab, when I will write, so again, let me go back to my pen. In the Scilab, I will be writing x is equal to, what is my row? Can someone tell me what was my row? It was 0. And then I have to give a gap and I have to write 1, followed by a semicolon. So whensoever one row is over, we have to put a separator to distinguish one row from another. So in this case, 0, 1 is my first row and then a semicolon and then 1, 0. So this is my X matrix. And then I am writing, say I want to multiply it on any state. Say I am writing state 0. So state 0 in my case is, say, another matrix, which is 1, 0. So, and then I want to multiply x star state 0. And this I want to evaluate. So what this command will do, this will multiply a matrix 0, 1, 1, 0 with a state 0, and 0 state is 1, 0. And that multiplication we can always check in the Scilab. So I am minimizing this particular window. I am escaping this window. First, I should close this and escape this and go to I should delete this first. Just a moment. Annotate. Cross. Cross is not doing that. We can move from this first. I hope some of you can practice this alongside. So let me close this and then go to another tab. Here in this tab, if you write online Scilab, this is a online cloud version which is available. This is Scilab on cloud, which does not need downloading. You just open it. And here, if you write a command, you can execute this command and you can get the results on the right hand side. Is my screen visible? Am I clear?
Yes, madam.
Yes.
Okay. So here I am writing x is equal to, what was my matrix? 0 with a gap, 1, then a row separator was semicolon, and then 1, then gap, 0, and then close this bracket. So this is my x and my state 0. State 0 is equal to another matrix that was 1 semicolon 0, and then I close this bracket again, and then I write x star state 0, and then I execute this command. Is my screen visible on the right hand side?
Yes.
What it
Under
is
the
doing?
result. Yes.
Are you getting the result? We had defined x, and then we had defined state to be 1, 0, and my answer is coming 0, 1. Can someone tell me what it is doing? What this operation is doing? Yes, yes, very nice. So it is doing a NOT operation in a logical or a quantum gate. Quantum gate, yes, you're right. So I will be going back to my slide. So here I will be re-looking at this particular slide again. That first we check that x is a unitary matrix by multiplying x into x dagger is equal to, we can do other way around also. We can find x dagger or u dagger into u is equal to I, where I is a identity matrix, and u is equal to u dagger is equal to u minus in the case if this condition is valid. You can always prove that these three are also valid. So we had checked that x, I had defined x to be 0, 1, 1, 0, and it is a unitary matrix. But how did I do that? I multiplied x by x dagger, and that was coming out to be an identity matrix. If that comes, it means that it is basically a unitary matrix, and all the logic gates or all the quantum gates have to be unitary in order to work for different applications. That is why the gates which we formulate should be unitary in nature, and we checked it for X gate. Is that right? So this is again the same thing which I have explained just now. This I have already done. So what is an identity? What is an identity matrix? Identity matrix is a matrix. This is a 2 cross 2 case in which we have got the diagonal element as 1 and off diagonal elements or other elements as 0. So now this is another example of a unitary matrix. So can you all try this unitary, whether this 100I is unitary or not? 100I. Should I go to that screen and demonstrate it for you? I can choose this pen. Yes, I am now choosing another gate, say A, which is nothing but 1, 0, 0 iota. So what was the first step? Take the transpose of A. So what is the transpose of A? 1 0 will become a column and this will become 0 I. And then I will take its transpose, its complex conjugate. So AT star, which is nothing but A dagger. And that is nothing but 1 0 0. I will be taking complex conjugate of the complex quantity. So iota here is a complex quantity. So I will get minus I. And now I will multiply A with A dagger. So A is 1 0 0 I and A dagger is 1 0 0 minus I. And the multiplication rule which we studied just now, 1 will go with 1 and 0 will go with 0. So I will get a 1 here. 1 will go with 0 and 0 will go with I. So I will get a 0 here. 0 is multiplied with 1 and I is multiplied with 0. So I get 0 here. And I, when multiplied with minus I, will make it minus I square, and I square is minus 1. So I will get a 1. So is it a unitary matrix? Is A unitary matrix?
Yes.
Yes.
Please write in the chat. Please, all of you. I should get 84 yes in the chat, or at least 50. And you should be convinced. It doesn't mean that you are just writing yes. It should mean also that you have understood it. Fine, fine. Okay, thanks. So I move forward now. I can stop my pen, turn off the pen, and move forward in the slide. So when we are simulating different gates in the IBM quantum simulators, I must tell here, there are very many quantum simulators are available these days. IBM is one of them now, but IBM is the most popular and most frequently used IBM composer or simulator is there, which is based on superconducting qubits. So in this case, there are some things which are by default. The qubit is initialized in 0 state and gates can be implemented on different states. Right now, just now we applied one gate to one state. What was that? I again write here. Just now we applied X gate on state 0. And state 0 was 1 0. What will be state 1? State 1 will be 0 1. So any gate, I had chosen a gate X gate, which can work on a particular state to yield a result. So what was X gate doing? It was negating, or it was taking that it was changing the state of the bit from 0 to 1. So same way, there are very many other big gates which can be implemented with the help of, there are inbuilt circuits there, and by dragging and by just pulling those gates, one can see how these gates are working. In this particular case, important thing also is here that this is called a block sphere. When we are working with one qubit, it is called a block sphere. And when there are more than 2 qubits, then it is called Q sphere. And that I will be just showing in the next forthcoming slides. Here, important thing is that like when we convert from the Cartesian to the spherical polar coordinates, we define a r as a radial vector, we define a theta, and we define phi. So in this particular case, when the qubit is basically, when there is a 0 state is there on the surface of this particular block sphere and 1 is downward. So one can always create different superposition state in this particular sphere, and that we will be just seeing in the forthcoming slides. Important thing here is also written, which I would like to highlight here. I would like to write that thing here, and that is the angle phi is given as cos of theta 2 in state 0 plus e to the power I phi sine of theta by 2 of state 1. So for different angles, one can generate different superposition states. And there are also rotations about x, y, and z. X's are also represented by different rotation operators. And rotation, I must tell you, is also one of the operation which can be facilitated through matrices. So with this, I will be moving on to showing to you that how does a output in a IBM Quantum Composer look like. So in this case, as I told earlier, that it is always is in the 0th state. So 0 here is being shown on the, say, on the top of the sphere by a blue circle. And there is a accompanying phase diagram which is also there. So if the phase, in this case, the color is blue, it is showing a phase that is 0. If the color becomes pi by 2, then if the color becomes magenta, then the phase is pi by 2. If the color becomes red, then the phase is pi. And if the color becomes yellow or light green, then the phase is 3 pi by 2. So this is for visualization. This is done. It shows probabilities and the state vector. So as I just told that it is the default state is the 0 state. So that shows that the probability of the 0 state is 100% and the state vector is in 0 state. Is this point clear to everyone, that we are seeing on the output a probability, a state vector, and a Q sphere? These all things will change when we apply a gate to a particular state. Like if I will apply a X gate to state 0 and 0 state is 1, 0, then my answer will be different. Is this point clear to everyone? Or should I again reiterate or retell this? I check the chat here. Yeah, I will explain it again. Okay. When we are working in the IBM computer that I will be showing, which is a virtually, you can say access that with the help of a login. I will be demonstrating that to you. In the beginning, the state is the 0 state and it is represented by a color. Color here is, and that color is representative of the phase. And in this case, when the color is blue, it means that it is in 0 phase. And when we apply different gates to these all three things will change. So there will be change in the probabilities, there will be change in the state vectors, there will be change in the Q sphere. That will be facilitated with the help of that gate on which we are working. In this particular case, I have applied identity gate. Identity gate does not do anything. It means that whatsoever is the position, that will be, it will stay in the 0th state with the 100% probability, and the state vector has got an amplitude of 1. Okay. And I think it will be more clear with the subsequent slides. So let me go forward in this. Just a moment. Let me erase this first. So here I will be using 4 gates or 5 gates, in fact, out of which some of these are called Pauli gates, which are single qubit gates. And I will be also using another gate that is called Hadamard gate. And as I told in the beginning, that I will also be discussing about a little bit about CMOD gate, which will be discussed tomorrow by Dr. Kiran. He will be talking what is the relationship of the gates with the phase. So I had shown one equation there that it is going to be cos theta by 2 state 0 plus e to the power I phi sine theta by 2 state 1. So depending upon what is the phase, you will see their position on that particular, say, sphere. So that I think will be more clear when we proceed a little bit more further. So in this particular case, these are the 4 polygates which can be handled with the matrices operation and also with the help of using them in the IBM quantum composer. Okay. So in this case, if I proceed further, this one I have already demonstrated that poly X gate is analogous to the NOT gate in the classical computing. Its action is to flip the state of the qubit. Did we get a 1-0 state after applying the X gate converted to say 0-1 state, which is 1 state? Was it demonstrated to you well? By in the case of the cylindrical coordinates and the spherical coordinates, the superposition states can be visualized in a much better manner because one can show different, say, orientation and rotations also. And in case one uses any other coordinate system, then all the hardware and software also has to be changed accordingly. And can we use the relation of phase and gates in classical computing that it is used in the bit when we are talking about bit in that case when we are using a NOT gate in that and we are not showing it in a block sphere and all, there we are only talking about numbers, that bit 0 will be converted into bit 1, but in this case we will see that many other things we are capable of doing. And that will be just demonstrated in the forthcoming slides. Okay. So in this particular case, is it clear to everyone that when we please don't scribble on the screen. Yeah, it could be by mistake also because all of you have access to use it. So in that case, please be careful when you are on the screen. So when we applied the X gate to a state, say 1-0, did we get a state 0-1? Just write yes or no in the chat so that will form the basis of understanding for the rest of the gates also. Akash has written S, so it means you are saying yes. Okay. Himnath, okay. Yeah, fine. Fine. Okay. Okay. So we saw that using a matrix multiplication that we were able to negate or we were able to take the inverse of that particular scale. Yes, yes, you're right. Okay. So how does it look like when we are applying this to our quantum computer? That is something interesting to see. We had seen the identity gate operation in that how would identity gate operation looks like. So if it was in the state, say 0, so it remains in state 0 with 100% probability and amplitude is 1. That is how it looked like. But when we apply a X gate, what answer do we get in a quantum computer is something which we will be just looking at. Okay. Okay. So here, what does it do? This simulation I have taken from a website, which is the resource of this is written at the bottom of this. So what it is doing, what XGate is doing, it is basically rotating in this and converting from 0th to say 1 state. And in that case, one can note down that this is your z-axis, this is your y-axis, and this rotation is about x-axis. Is it clear from this simulation? That how a poly X gate is converting a state 0, which is represented by a state 1, 0 in the matrix form, to a state 1. Is this point clear? Or should I make it more clear? Please write in the chat. Okay. Okay. And how much time do I have? Dr. Reshma, how much time do I have?
Yeah, 20 minutes.
I'll try to finish in that. So what X gate is doing? Again, I am showing, I am reconsolidating on that X gate is represented by a 2 cross 2 matrix, that is 0, 1, 1, 0. When it operates on a state 1, 0, which is a 0 state, it converts into a state 1, which is 0, 1. And if I will do the other way around, if I will have a state 1, it will convert it into state 0. So this is doing flipping of the states from 0 to 1, and that is what it is doing, and it is incorporating a rotation about x-axis. That is why the name is such. This demonstration I will come a little bit later. Let me go forward. So X working on 0th state is converting it into 1 state. How will it look like in the IBM computer? This is what I would like to show here. And if any one example is clear, I am sure that you will be able to understand rest of the example also very clearly. So in this particular case, what is happening now? The probability which was 0 in the beginning is now 1. And this probability is 1 for the state 1. Whereas the default state was 0. So there in the 0 state, the probability was 1. Now it has changed to 1. Did you remember that blue color arrow was towards the 1 state to begin with without applying the X gate? Now it is downwards. So in this case, phase remains the same, that is 0 only. And one can always work out the fine. In that, you can always see the state, and you can always stick out the phase angle also. So all this can be viewed in that computer, in the composer, IBM composer, which we will be just looking in a few moments from now. Okay. So here, actually, when you write on this, then in that case, every time it has to be cleaned, then only it starts going forward. Okay. Now my question would be, if I apply X gate twice. Suppose I want to apply on 0th states. Again, I am choosing my pen in order to make it more clear. So if I do this operation, X, okay, this part of the board does not work for me. X, 0 is question mark. This is my question to you. How will it look like? What will be the answer? Please write in the chat. So one X working on state 0 will make it state 1. And when another X is working on state 1, it will make it back to state 0. So two successive operation of X gate twice will make it back to the same position. Okay, that can be viewed in the next slide, which I am going to show just now. So one can see here that you are back at 0th state with the probability as amplitude as 1 and probability as 100%. So a successive in the simulator at this is a, can you see Q0 plus plus? So plus sign is a sign for a X gate. And when you apply this twice, then when you simulate, you get this kind of answer. And that is actually a demonstration of double, say, X gate. Now is another gate which comes at Z gate. Z gate is represented by 1, 0, 0, minus 1. So in this case, when you multiply it with the state 0 is 1, 0. Should I do it here or you can understand yourself? Please write in the chat. Is it obvious that you can do this or should I do it for you? If I do this, what do I get? As I told, multiplication we go like this. So 1 multiplied by 1 and 0 multiplied by 0. So I will get 1 on the top and 0 multiplied by 1 is 0. Minus 1 is multiplied by 0 is 0. So I am getting back the same state if I am working on state 0. So it says that state 0 goes to state 0 only. But when you will take 0, 1 here, then you will get a negated state of 1. So the poly Z gate is also known as a phase flip gate. Its action is to flip the phase of one state but leave the state 0 unchanged. Am I clear? Okay, you can do it. But for the benefit of everyone, I have done it. So I think by doing this twice, it should be clear. That is what I assume. That is why you should be ready to do it for the next one if it is clear.
What is the meaning of negative? Why the negative sign? Negative 1.
In
Why
this
the-
case, it's amplitude. I will show you in the next slide. Please wait. That will be clear from the next slide. Just a moment. Let me clear this again. Or best would be to see the matrix multiplication simultaneously so that one can understand that more better. So if I do here 1, 0, 0, minus 1, and suppose it is working on state 1 and state 1 is 0, 1. So can someone tell me the answer? What will be the answer? 1 into 0 is 0, 0 into, so I'm getting here 0 on the top. And here it will be 0 into 0 and this will become minus 1. Can you see the change here? That state 0, 1 is converted into state 0, minus 1. So how will it look like? Its phase will change and that will be seen in the next slide. Just a moment. So can please see this simulation and also see what it is doing, that it is hovering over, changing the phase from along the along this z-axis, and in that case the plus state is changing to the minus state. So in this case, if I take the convention to be, say, positive, convention can be clockwise and the anti-clockwise. So one can see that it is going the other way around, and that is what it will show. And if I go to the next slide, I think it will make it even all the more clear. This I have already done it myself, so this part is done. But I would request everyone to try this in the Scilab also, so that one can always see that these codes you can write very easily in the matrix form. Okay, this is how it looks like. So if I am applying a Z gate, in that case, the state zeros remains the same. There is no change in that. And if I do it on state 1, then it will look like this. Can you see the phase change of this? Of the one state? It is showing red now. So red is meaning that the phase is it clear?
Yes, ma'am.
Okay. So actually, if you see, there was a factor of e to the power minus e to the power I pi. And that introduces, that is nothing but cos pi plus iota sine pi. So in that case, when you see, convert that into the phase is showing a red color now. Previously, it was blue, even for the one state, state one also. So it is introducing a phase change in the one state, but keeping, it is rendering the state 0 as it is. So this is what this particular gate is doing. And next we move on to the next gate, that is the Y gate. So this is poly Y gate, which is 0 minus I 0. If you do this operation, then it will convert 0th state to I times 1 state and 1 state to minus I times 0 state. So it is doing, it is flipping the state of the qubit and it is changing its phase also. So this can be taken as a combination of X gate and Z gate with an additional I phase. So this is also called as a bit and phase flip gate. And one can see that it is showing a rotation about y-axis. That is why the name is Y Pauli gate, and this is how it is doing. And if I see its operation, if you take this gate 0 minus I 0, and it works on state 1 0, you get 0 I. And if you do the other state, then it is minus I and 0. And Suhail, I would request you not to scribble on the screen. Please don't do that. And in the case of now, can you see the color here? That color is, say, magenta color here. So there is a phase change of pi by 2 in this particular case of the state, which is original state was basically we are applying the Y gate. So in this case, if I am applying on the 0th state, it is converting it to I and then the 1 state. So there is a phase change of pi by 2 and 0 is getting converted into 1. So this is how these three gates work. Other than that, there is another important gate which is called Hadamard gate, which is very, very important gate because this gate is useful for converting a 0 or a 1 state into a superposition state. So if you do this operation, this is given by 1 by root 2, 1, 1 in the first row and 1 minus 1 in the second row. And if you do this operation, you will be getting a state which is actually a combination of the two states, and that is called the superimposed states. And in this case, one can see that it is having a it is not only about X or Y or Z, it is actually a combination of all of these two states, and that is what it does. And if you see, if you are getting here output, if it is working on the 0th state, you are getting 1 by root 2, 1, 1. That is similar to the things which we have done under 1 by under root 2 of the 0 state plus 1 by root 2 of the 1 state, which is a superposition of the two states. And if it is working on the 1 state, then it will produce 1 by root 2, 1 minus 1. So that will be 1 by root 2 state 0 minus 1 by root 2 state 1. So in this case, it will look like when you apply this gate on the quantum computer, it will look like the computational basis states are basically 50-50 in this case. So earlier it was having either 100% one state or 100% say 0 state, but here the probabilities are 50-50, but the amplitudes are also equal, but they are not actually 0.5. This is having some other number. Can someone tell me that what is the difference here in the probability and the amplitude? It is having some value which is not 0.5. So actually it is 0.707. So if you remember, one is alpha, and alpha square is the probability. And when you are writing it in the state form, it is basically alpha. So it means that one has to take the under root of this quantity. And here the states is having a phase 0, and it is both the states are available here, 0th state and the 1 state, and that is what is the superimposed state. So this is something which is very importantly used in that. If I apply a NOT gate, say X gate followed by a Hadamard gate, then what will be the change? One can work one can do this using a Scilab problem, one can solve the matrices by hand, and then one can simulate in the IBM quantum simulator or composer or many other, as I told, are available in order to see what changes will happen. And if I'm using two Hadamard gate together, then what should it look like? That all can be, say, how would you know you are getting a correct answer or not? So we need to first try it manually, then try it using Scilab code or any other mathematical code. And thirdly, I need to simulate it and then try to see whether I am getting the situation which I should get or not, in order to validate the theoretical and the observed things hand in hand. Okay. I would be also tempted to use this, because tomorrow's class is going to be based on this. This is called a controlled NOT gate, which is given by this kind of a symbol. So right now we were just dealing with 1 qubit or single qubit. When we increase the number of qubits, then in that case, right now we are using, the gate was being represented as 2 cross 2 elements. What will be the number of elements of such a gate which is handling 2 qubits? So in that case, this I leave as a question to think about, and moving further on, because this will be done tomorrow, so you need not worry about it. But if I introduce something today, at least tomorrow you can come prepared, or you can read about it before you come to the class, or you try to explore more things related to that. So with this, I think I am on verge of completion of my slides. Let me see that. Okay. This is a simulator example of the CNOT gate, which I am again skipping for the time being, because as I'm telling, this will be done tomorrow. So you need not worry about it, but at least get in familiarity with the terminology and the metrics which is representing that particular gate. Okay. So now I can show you the quantum computer, that how one can build circuits in the quantum computer. So this is our IBM virtual quantum computer, which is very popularly used by different students as well as faculty members across the world, not only in India, everywhere. So here in this case, when I have chosen just single qubit here, Q0, it can be labeled any name. These are the different symbols of the gates which are available. So Z is clearly visible. It is written by the name Z. This gate is the X gate, which I have just pulled in. And then there is also a gate called Y gate, which we talked about. Y gate is also there. There is another gate which is called I gate, which is the identity gate. And we also talked about this red one, which is called the Hadamard gate. Other than that, many other gates are also available. People are trying, everyone is trying to utilize. Am I visible? Is there any, am I audible?
Yes.
Am I audible?
Yes, you're audible, ma'am.
Okay, okay. State here would
You
mean
are.
that Merush, state here would mean that that state, 0 states and 1 state. And when we are talking about quantum computer, we are talking about their, say, combination, their superposition. So that is what we mean. So when I am saying, say, 0, 1, 1, 0, These are representing the probabilities in the state, say, 0 and 1. So if my state is 0, it means that the probability of being occurrence in the 0th state is 100% and in the state 1 is 0%. So it is like that. I hope I have answered your query. And other than that, here one can see, I would like to show you that if I have applied here one NOT gate, then in that case, I am getting a state, original state was 0 state. Please remember that IBM computer ka initial state is the 0 state. So when I have applied a NOT gate, or sorry, X gate, which is actually acting as a NOT gate, so your state is now one state. So it has converted from 0 state to 1 state, but still the phase is remaining to be 0 only. Okay, because it is showing a blue color and there is no phase change occurring. If I now try another, say I pick it up, is my screen, toggling screen visible? Am I, that I am pulling another gate? Is it visible?
Yes. Yes,
Okay.
ma'am.
So now I have got another gate on this. Can you see the states has changed? Now it has come back to the 0th state. The probability now is 100% in 0 state. And it is the amplitude in the 0 state has become 1. Am I right?
Yes.
Is it clear?
Yes.
Okay. So with this, I think I can go back to my slide. Thank you. I have already done. And I would like to, these resources which I have just shown here, I will be sharing all these resources, these simulations and everything as I have been doing, I'll be doing for this session also. And I think you can ask, I have been answering the questions in between, majority of the questions, but still if there is any left, I would be happy to answer. And other than these, every country is making their own quantum computer. And in those quantum computer, they are having, say, different types of qubits. In this, as I told you, in IBM and in many other computers, superconducting qubits are being used, but in majority other even trapped ions are also used. So depending upon which basically company is making it and what type of qubits they want to practice on or they want to make on, there it is getting changed, and that is how we are having and everyone is trying to use reversible gates in this. Reversible gates are the gates which have got equal number of inputs and equal number of outputs. In that case, whatsoever errors are there from going from input to output, those errors handling is they are trying to optimize with the help of reversible gates. So with this, I would say thanks again to all the participants and all the stakeholders of the organizers and the organizers. Thank you so much.
Thank you, ma'am. That was a really very nice presentation on quantum gates. If there are any questions, you can unmute and ask, or you can type it on the chat box.
There is a necessary condition when you are physically working on a gate, that unitary matrices are basically all the logic gates, all the quantum gates follow this say unitary operation as one of the basics for implementation, and that has got physical say meaning also, and that is why all the gates which are there should also follow that. Okay. Is there any classical analog of Z gate? In the classical, we know about gates like AND, or NOT, NOR, NAND, and XOR gate. So there can be many gates can be made in combination also, and those can be basically compared in the classical as well as in the quantum modes. But all these gates are quite unique, and in this case, many other because I have not touched upon all the gates. I have just explained very basic say gates in this. Firstly, I must stop sharing in order to share the link of the quiz, or I can do the otherwise also. Just a moment. So I have to share this in the chat. please find the quiz here and please take 15 minutes in order to answer that. Should I stop sharing, Dr. Reshma?
Yeah, I think that will-
Okay. Stop share.
yeah. So if there are any questions, you can still ask. There was one question in the chat box in the beginning. What is the relation between phase and gate?
Phase and
Gate.
as I explained in the block diagram in that block sphere, one can always say convert these spherical polar coordinations, and those are represented as say theta and phi. So theta and phi would mean that about which axis we are rotating, and we can always relate it to x, y, and z directions. And depending upon that, what are our basically what are our requirements or what a gate is doing, that can be represented. So in this particular case, it is actually cos theta by 2 plus e to the power I phi sine theta by 2, and the cos theta by 2 is multiplied by state 0, and the other factor is multiplied by state 1. So in this particular case, one can represent, this is a visualization for even to visualize the superimposed states also.
Okay. So there's one more question here based on the simulations. Can we make a quantum switch for a specific function by these simulations?
Which it will depend upon what kind of switch we are talking about. When we are talking in the classical systems, actually transistor is acting as a switch. Like when we are giving input high, it turns it to low, and other vice versa. So it will depend upon the requirement that what kind of switch, and definitely we can make switches here. And if we are, because we are able to invert the phases as well as we are able to invert the states also. So in that case, bit inversion and the phase change, these two are getting accompanied, and depending upon our requirement, I think this can be done.
Okay. Pauli gates that you introduced, is it another name for Pauli spin matrices?
Yeah, it is actually using that. It derives its composition from there, and depending upon which direction we are wanting that rotation to occur. So depending upon that, these have been named. And if we don't want anything to be done, then identity gate is the one which is used in this regard.
Okay.
But
So
this is not a complete story of the gate. This was just a brief introduction. There are very many other gates. And as I told that there is recently I read a paper a few days back that people are trying to basically convert all these gates into reversible gates, so that will help in their in minimizing or optimizing many things. So actually, and that those things people are trying. So that gate would have equal number of inputs and outputs, and whatsoever is there going from input to output can be reversed back also.
okay. Thank you, ma'am. Are there any questions? We still have time.
Ma'am, I want to ask a question.
Yeah, please go ahead.
Ma'am, in classical computing, we use transistor to make gates. But how we realize quantum gate in practice?
This part will depend upon what kind of quantum bits we are using. If we are using superconducting bits, so in that case, those bits should be able to create the situation of superposition or entanglement or of other things. So that hardware, as I told, you need to have knowledge about the electrical circuits, resonances, how to manipulate those using say micro cavities and microwave cavities and all that. So those advanced things for seeing the background of all the students, and we are having a mixed background, so we are not going into that much detail, but this can be realized by choosing the type of quantum bits which I have named many times in the slides also.
Okay, ma'am, thank you.
Any other question?
I would also like to. Yes, please continue.
Can you repeat how to check whether the matrix is unitary or not?
Yes, I can do that. first take the matrices and do its transpose. Transpose is converting from rows to columns and columns to rows. Rows to column. Like if there are 2 rows,
Right.
you convert it into column. And if it is having any complex part, then you take its conjugate. Like if it is iota, as I showed you in one of the example, one of our metrics like X matrix was not having any complex part. So in that case, after transposing, there was no change if I was taking the complex variable. But if there was I, in that case, you have to take its conjugate, that will be minus iota. If it is minus iota, it will become iota. It's like that. Can you, if I ask you that what will be complex conjugate of 1 plus, say, AI? So it will be 1 minus AI. Okay, complex part has to be, imaginary part has to be taken, its conjugate, real part will remain the same. After that, you take the original matrix and multiply that by this transposed conjugate matrix. And see whether you get a identity matrix or not. If you get an identity matrix, it means that your matrix is a unitary matrix. And in Scilab, there is a command prime. If you take a prime command, then it is doing both the things. It is taking transpose as well as it is taking complex conjugate also. So today, because of the, say, scarcity of time, I think there can be more extended, say, computational hands-on also, because that is something which is also need of the hour in order to understand this field.
Okay, thank you, ma'am.
Okay.
Yeah. Is there anybody else who wants to ask question to ma'am?
I would like to only add this, that many companies keep on doing internships. Our Kulkarni sir has also keeps on sharing in the group. So you can always, all of you can always look for those internships by IBM and many other companies. Even IITs, ICERs, and many other central universities are also offering these internships and summer schools, which can give, if you are interested in this field, definitely you can get extended knowledge and you can read more about it and you can practice it. And as I also explained, it is an interdisciplinary field, so you need to have many more other domain knowledge also. Thank you.
Yeah, thank you, ma'am. Okay, Kulkarni sir has joined us from very far.
Yes.
I invite sir to say few comments.
Yeah, I just want to, as a convener, I am very happy to see about 85 to 90 persons interacting. Beautiful explanation by Professor Vandana Madam. I also feel that about half the crowd might feel a little uncomfortable with the mathematical part, but they should learn to do this simple mathematics. It is not very complex mathematics at all, very simple. You need to understand the basic rules of the game and learn the operation. Once that is done, I think it will be easy. And it was so nice of Professor Vandana to have explained patiently all the questions that went for about 20 minutes. The pleasure in seeing the questions because people are that is a proof that students who have joined here are really trying to understand. And as Gita ji says, Pariprasnena Seva. When Gita ji says Pariprasnena Seva, they mean that those who ask questions and get their answers clear are the real students. And I'm sure it has been possible for all of you, Reshma ji and Madhusudan and Professor Balakrishnan and Vandana, to have put together a wonderful team. And I'm happy to see you things happening from about 13,000 kilometers away, sitting in Texas. Thank you very much. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you,
We
sir.
are happy to see you too.
Thank
Okay.
you.
Yeah.
Yeah. So, ma'am, thank you very much for the session today. I don't see Luvalia sir today. I think he's somewhere else. So,
Yeah.
I must say, yet another feather in the learning of quantum computing for us today. That was on quantum gates. So, ma'am started with a nice quote by Feynman and also revised what we have learned earlier with respect to the quantum computation in this workshop. So today we had an introduction of quantum gates, especially Pauli Y gate, Pauli Z gate, control not gate, and Hadamard gate. We have seen some beautiful simulations using Scilab. We have seen how to change the state using quantum simulations, and how does a quantum composer works. And finally, ma'am has shown us how to build a circuit in quantum by using a quantum computer. Thank you very much, ma'am, for sharing this knowledge with us, and thank you for answering all the questions very, very patiently. Thank you to all the participants for being in this session, for being 100% present in this session, and taking part in the discussion along with the ma'am. Thank you, ma'am. And now I hand over to Dr. Madhusudan.
Thank you, Dr.
Reshma ji.
Reshma. Thank you. Thank you so much.
Thank you, Reshma ji. You hosted today's session in a wonderful manner. And I also thank Vandana ma'am for
Thank you.
very nice presentation on quantum gates. For the benefit of the participants, we have shared the YouTube links of 5 earlier sessions so that you can review and gain additional inputs from the recorded lessons, and also from the question answer sections at the end of each session. Okay. With these few words, I thank both Reshma ma'am and Vandana ma'am for today's session. And I also thank all the participants for your patient participation. With this, let us wind up today's class, and see you tomorrow at 6:30 p.m. Thank you, one and all.
Thank you.
Thank you so much. Thank you so much.